So welcome everyone to this Meow seminar, and it's a pleasure to have Siddharth Iyer here, who will tell us a little bit about XOR lemmas and communication complexity.
Thanks for coming. Thanks for inviting me to the talk. Just let me try to figure.
Maybe enter.
Enter. All right. Yeah. So I'll tell you about some XOR lemmas and the listing theorem in communication complexity today. And please feel free to interrupt and ask me questions. I want to go slowly, and hopefully everything makes sense and it's clear. Okay, so let's get started. So, so the theme of the talk will be around the following type of questions. So, how much harder is it to compute n copies of a function if in terms of n and the hardness of computing a single copy? Right. So this is one of the type of questions that we'll be interested in. And certainly, if you have an algorithm that computes a single copy, you can run it n times, and with a blow-up of n times the resources, you can compute all n copies. This is certainly possible, but is it really necessary? And can we have clever algorithms? So that's one thing. And another question is, maybe we don't insist on computing all n instances. We just want to compute a function on the outputs of the n instances. So, and so the way I've stated both of these questions, they're quite general. You can ask them for several different models of computation. And it turns out that in some models, there are actually clever algorithms that give you savings on computing n instances over the naive way to compute it by repeating n times. And in some other models, you really need a lot more resources to compute n instances over a single instance. Okay, so we'll be interested in this question in the model of communication complexity. And before I tell you about communication, etc., I want to zoom back and give you some motivation for why this question is really interesting in complexity broadly and theoretical CS. Okay, so I'll give you a few examples, and then we will dive into communication complexity and this question in particular. So the first example, it's actually an example of a function. It's actually an example of a task for which you can compute n copies much better than computing, repeating the naive computation n times. And this example comes from matrix multiplication. So here's a fact. It is that there are n by n Boolean matrices A, such that if you want to compute the matrix vector product AX, you need circuits of size n squared over 9. This is a counting item. Now, what about computing the matrix vector product n times? So note that computing n matrix vector products with the matrix A is just a matrix multiplication operation. And there are much faster algorithms to compute matrix multiplication to compute the multiplication of two matrices over repeating a single matrix multiplication operation n times. So we have algorithms that run in now n to the 2.3 times. So here's an example where you get savings. And another example is what's called an XOR lemma, which is going to be relevant for this talk. And this comes from cryptography. And this was discovered by Yao. So Yao's lemma, XOR lemma says the following. So if you have a function f with the feature that circuits of a certain size s, they fail to compute f with probability much better than 2/3. Then slightly smaller circuits of size epsilon squared s, they'll fail to compute the XOR of n copies of f. So now I'm assuming f is a Boolean function. They'll fail to compute the XOR of n copies of f with probability much better than random guessing. So if epsilon is sort of sufficiently small, this right-hand side will be like half plus something that's exponentially small than n. And you can't, yeah, so to compute the n-fold XOR, so this I'll call this XOR of n copies of F, the n-fold XOR, you really can't do much better than this. And a corollary of this is that the existence in cryptography is that the existence of weak one-way functions also implies the existence of strong one-way functions. And one-way functions are basic cryptography. So that is, and this is called an XOR lemma because it relates the hardness of computing the XOR of n copies to the hardness of computing a single. So, and another sort of example comes from trying to resolve the Boolean depth conjecture. So, another fact is that Boolean circuits of small depth have small size. So if we have depth d, then we have size roughly equal to d. And we can ask if some kind of converse holds. So if I give you a polynomial size circuit, can you simulate that computation with a circuit of logarithmic depth? And we believe the answer is no. And a way to show this was suggested by Kashmar, Raz, and Richardson, 91. And they said, let's take a random function on log n bits. If such functions can be computed and really require circuits of size roughly n and depth log n. And now let's compose this function with itself recursively several times. So in this picture, f has log n inputs, and for each input, we will plug in another copy of f. And we'll keep doing it some number of times. So the number of times we will do it will be roughly log n divided by log n. So some number of times. And what we can show is that at the end, the resulting function can be computed by circuits of polynomial size. But if you naively repeat the computation for f, like you plug in this basic circuit for f in each of these circles, you will get super logarithmic depth. And the conjecture sort of is that you can't really do better than that. So in particular, if you can show lower bounds for circuit depth, when you recursively compose, you'll be able to resolve this conjecture. And this also is a good segue into communication complexity, because depth lower bounds for circuit corresponds to communication lower bounds for a special type of communication game, which I will tell at the end. And so if you get communication lower bounds for some special type of games, you also get depth lower bound. So yeah, I hope these type of questions are interesting, motivating enough. And with this, I can now try to tell you more about what we do for these questions in communication context. Okay, so just an outline. So first, I'll tell you about the model of communication, and then I'll tell you the results. Afterwards, I will tell you, try to give you a sketch of the proof of this theorem, which I'll tell you what it is. Following that, we'll discuss the randomized XOR lemma, and if we have time, we'll talk about this quantity called marginal information, which is a sort of new measure of information that helps us get this XOR lemma. And then I'll end with. So what is communication complexity? So this is a model of computation where there are two parties, and let's say they want to compute a Boolean function that depends on each one of their inputs. So in general, they are also interested in computing functions that are not Boolean. But for this talk, let's stick with Boolean functions. And so the way they compute this function f of xy is they're going to communicate with each other. So, and this communication will be specified by a protocol. So Alice gets an input x, Bob gets an input y, and this protocol will specify how the communication works. So Alice will start the protocol by sending a message to Bob, and this message depends on her input. Then Bob will respond based on that message with another message. And this interaction will go for some R rounds. at which point both parties know f of xy and the protocol ends. And the length, there are going to be a few quantities that we are going to be interested in with communication protocols. One is the length of the protocol. This is the maximum communication that the parties incur in any execution of the protocol, the length of pi. And the deterministic communication complexity of f, df, and this is the length of the shortest protocol that computes. This is communication complexity. And we can also ask what we get if we allow the parties access to shared randomness and private randomness, and how that, and allow them to make mistakes. So that is randomized communication, which is more powerful as a model, and but the picture doesn't change by too much. So in this model, the parties have access to a shared random string as well as private random points. At any point of time, whenever any party is sending a message, they can look at the shared randomness and as well as flip some random coins. And depending on the outcome, they can decide what message they want to send. So again, the length of pi will be the communication, the worst case communication, the protocol. I'll use this notation later on, pi xym, to talk about the distribution induced by pi. Like, so right now, so later on we'll have x, y, these inputs are coming from some distribution, so that makes sense. And finally, the success probability of the protocol. So fix a protocol. The success probability of the protocol is the worst case success probability. So we'll say it has success probability 1 minus epsilon if the protocol succeeds to compute f with probability 1 minus epsilon on every input. And this quantity, success probability of f, to be computed by c-bit protocols. This is the maximum success probability you can achieve if you're allowed at least c bits of communication. Good. So this is randomized communication. And I want to talk about a couple of nice facts about communication, and then I'll tell you some background and the results. So one nice fact about this model of communication, and it's an alternative sort of view to communication protocols, is that so let's say we have a deterministic protocol. So the messages of the protocol, they partition the space of inputs into monochromatic rectangles, and I'll tell you what I mean. So let's think about this box. So this box is like you should think of it as a matrix. There is a row for each input of Alice. There's a column for each input of Bob. And the entry in the row corresponding to row X and column Y is the function. And so let's see how a protocol looks. So Alice starts the protocol by sending a message. And this message partitions the space into two blocks. So if Alice's input is in the top block, she sends 0, say. If it's in the bottom, she'll send 1. Bob, based on whatever he receives, will further partition the space of messages. So if Alice sends 0 and Bob sends 0, maybe he'll go on the block on the right side, and he's right from me, and otherwise on the left. And the same thing if Alice sends him 1, and this sort of keeps going on. So every time each party sends a message, they refine the space and they further partition it. And at the end, the players know the function value, so that the final rectangle that they arrive at must be constant for the function, because they know the function value for every input in that rectangle. Okay, so that's how a protocol looks in this matrix. Another nice fact is that so later on we'll work with probability distribution, where the inputs are coming from some probability distribution. So if this distribution has the feature that it's a product distribution, then conditioned on any rectangle, this product distribution feature is preserved. So for example, if the inputs are uniform, then the inputs still remain independent, conditioned on the rectangle. And that's simply because the rectangle is a Cartesian product of rows and columns. Okay, so these are like two nice facts about communication, and I'll just call them out later on. Okay, so let's now move to some background. So let's first see what we can say about the complexity of, like, trivial bounds on the complexity of computing the n-fold XOR or the n-fold repetition, which I'll tell you what it is. So this is just a notation that maybe I didn't say what f superscript XOR n is, but it's exactly this. Take the XOR of n instances of f. And df, as we've already seen, it's the deterministic communication complexity, and this is the success probability to compute f. So the first observation is that you can compute the n-fold XOR of a function with, as well as the n-fold repetition of a function, by just repeating the best protocol, best deterministic protocol n times. And the communication complexity is at most n times the deterministic communication complexity. So this is a basic bound. And similarly, we can ask, what can you say about the success probability of computing the n-fold XOR if you're allowed n times c communication and you just repeat the naive protocol n times? So it turns out that the success probability looks like half plus some number which is exponentially smaller than n. Okay, so this number 2 times the success probability of f for c-bit protocols minus 1. It's a number between minus 1 and 1. And it's, so this to the power n makes it exponentially small. Okay, and to see why this is the case, it's good to think about a slightly different quantity, which is called the advantage. So fix a protocol pi. The advantage of pi to compute f is this expectation. So this expectation, it's 1, it's over the randomness of the protocol. And it's 1 if the protocol succeeds in computing f, and it's minus 1 if it fails. So it's this number between minus 1 and 1. And it's going to be large, and it's going to be close to 1 if on every input, the protocol succeeds with good probability. And if the protocol is doing something very silly, like outputting a random bit, then this number is going to be 0 because it's not correlated with f at all. So this is sort of how biased the protocol is, how correlated it is with the function. And if you rewrite this, you can see that this is 2 times, and this number is now the success probability of f minus 1. The great thing about advantage is that if you take the protocol pi, repeat it n times, and take the XOR of the outputs in each copy, then the advantage of that protocol tau to compute the n-fold XOR is the nth power of pi to compute f. So the advantage just keeps multiplying when you repeat the protocol. And I won't show it, but it's basically just this expectation. It looks like an expectation over n independent instances, and you can write that as a product of that's the I. That's sort of high. So this advantage quantity is very nice because of this multiplication structure. And going forward for the randomized part of the talk, I'll use this notion advantage. So basically, I'll just replace this quantity on the right-hand side with advantage. Convenient. Questions about the notation or question? Okay, so now I can tell you the result. So first I'll tell you the randomized XOR lemma result. So this is just the notation that we set up. And just like we defined the success probability to compute f with c bits, let's talk about the advantage to compute f with c bits. This is the maximum advantage that you can have as well if you're only ever allowed c bits of communication. So with this, I can tell you the result. So Anup and I had shown last year that there is an absolute constant C0 such that for all C, at least C0, if you need, if even with C bits, you cannot have advantage better than some constant 1/3, then to compute the n-fold XOR with exponentially small advantage, the sort of advantage that you get by repeating n times, you really need at least root n times the communication lower bound. So I'm going to pause here because if you repeat the naive protocol n times, you get the advantage is exponentially small, like we had seen before. The lower bound we're able to prove is that you need communication at least square root n times. Okay, so this is the result. So if you state it differently in terms of success probability, you can show that the success probability to compute the n-fold XOR, even with root n times c bits, is half plus exponentially small. Yeah.
Just wondering, are there like upper bounds where you can do better than n times c?
There are for the direct sum there are. There is a separation of this information and communication thing that gives you some savings. Yeah, so I think there are, but I think it's only like a log, a little log.
To compute target, you do this for free.
Yes.
Yes.
So for parity is also a good example in this case to think about because you can compute the parity of 2 bits with 2 bits of communication, but to compute the XOR of the parity on n instances, also you can do with 2 bits of communication. And so you need some kind of this type of hypothesis that C needs to be sufficiently large to make a statement that's coming. Okay, so now and afterwards we showed a deterministic XOR lemma, so deterministic communication. So again, this is the n-fold XOR notation. And here we showed that, again, there is a constant C0, such that if F requires at least C0 bits to be computed with deterministically, then to compute the n-fold XOR, you need something that looks like every protocol has to have communication, which is at least n times the quantity that looks like the communication of F divided by log of the rank of F. I haven't told you what rank is, I'll tell you now, but roughly looks like this quantity. So the rank of a function is a nice quantity. It is very related to communication as well. It's the rank of the matrix that I told you before. So there is an input for each row of Alice, and there's a row for each input of Alice, and a column for each input of Bob. And the corresponding entry is 1 if f of x, y is 0, and -1 if it's. Okay, so rank of f is the rank of this matrix. And rank and communication are related. So we know that communication has to be at least the logarithm of the rank. So, and the log rank conjecture, which is open, it asserts that the communication can always be bounded by some polynomial in the log of the rank. So that's how they're related. And one sort of corollary of this, is that this was observed by Young, which is that he observed that the rank of the n-fold XOR of f is really the rank of f to the power n. So when you take the n-fold XOR, it just corresponds to tensoring this matrix. And so the rank becomes the rank of f to the power n. And using that, you can actually conclude that, and using that fact and using this theorem, you can conclude that the communication complexity of the n-fold XOR is at least n times square root of the communication complexity of f. And the basic idea is that you just do it by cases. If the communication is like at most log squared of the rank, you're going to use the fact that the rank tensorizes. Otherwise, you use sleep. So that's the deterministic XOR lemma. And we generalized this earlier this year, and this is a sort of lifting theorem. I'm going to tell you what it means. So now, so previously we had the XOR of n copies of f, and now we can ask, what about computing some arbitrary Boolean function g that depends on the outputs of each copy of f? And here we can say that if, again, the communication complexity of f is some sufficiently large, at least some sufficiently large constant, C0, then to compute the composition of G with f, you need the sensitivity of G, so S of G is the sensitivity, which I'll tell you what it is, times the same quantity that appeared before, the communication divided by the log of the. And the sensitivity of G is the maximum sensitivity it has at any point, where the sensitivity at a point is the number of coordinates with the feature that if you flip only that coordinate while keeping the rest the same, the function already flips. So previously we had G being the parity function, and the parity function has sensitivity n at every point. If you ever flip a coordinate, the function value will change. But you can get sort of the same result for OR and or in general for functions with sensitivity s. So that's this, and a corollary of this, again using the same idea as now, is that again, if f has communication complexity some sufficiently large constant, at least some sufficiently large constant, then to compute the composition, you need communication which is at least the minimum of the sensitivity and a quantity called the degree of G. Degree of G is the degree of the real polynomial that computes G. So you can always write G as a real multilinear polynomial, and degree of G is the degree of that polynomial that computes G times square root of the deterministic communication.
How does this compare to, I'm trying to relate this to like Gös-Pitassi Watson style results.
Yeah.
So there you actually carefully fix it. So F will be the gadget here.
Very good, very good. Yes. So
and here you're just saying like any gadget for which I have very general.
Yes. So traditionally in lifting theorems, you fix the function f, and you want like really strong word bounds for the composition with any g. And lots of results give you a quantity here that's much better than sensitivity. Like they give you decision tree complexity, which is sort of the right measure. But however, they only work when the gadget size is sufficiently large. Here, we don't make any assumption about the gadget, but we don't get decision tree complexity. Another thing to
I mean, how far? Sorry for my ignorance, but like how far off with sensitivity and decision tree?
Yeah. So the sensitivity is at least the sixth root of decision tree complexity. So all these quantities, sensitivity, degree, decision tree complexity, they're all very related. And yeah, so sensitivity is at least the sixth root. I should say, so for some gadgets, this can be further improved. This can be improved to this quantity called the block sensitivity. And if you like really fix the gadget, for example, F to be the inner product gadget, then actually you can get sensitivity times the deterministic communication complexity divided by log of the deterministic communication. There's no rank term, just log of the deterministic. So, yes.
This kind of local, like if you assume G is just partially defined and where the sensitivity is happening, still true?
So I thought about this at some point, and I want to say yes, but I have to double check. The proof, yeah, I mean, I'll show you the main aspects of the proof. It actually just uses the sensitive inputs.
Yeah.
It doesn't use the yeah. And so that is the, yeah.
And what's the upper bound we know?
Yes, good. So any composition can be computed with communication decision tree complexity of G times the communication for F, because you just, so the decision tree will give you the path that you want to go. Every time you query, you'll compute it in that coordinate. So like if the decision tree wants you to know the function value at the first coordinate, you will just outright compute the first coordinate and then keep going based on what you.
So what you're saying also then is that maybe modulo checking, like if G is a relation and I do this critical sensitivity or block sensitivity, things might also work.
Yeah, this works for. So I think it works for like critical block sensitivity, but I have to double check.
There are some people who use this in the context of proof complexity.
Questions?
Yeah, and kind of just like this. Is there like a reason to see why sensitivity shows up?
Like say
small intuition of it. Why sensitivity?
Why sensitivity is sort of the right measure. Well, so I'm not claiming that sensitivity is the correct measure that should show up here. It's the most sort of the only thing I can say is that if you really have a point which is sensitivity n, so like let's say the sensitivity is n at all zeros, then you have to compute the all zeros correctly, but and you have to no matter how, if one of the coordinates changes, you'll have to sort of for every flip at that coordinate, you have to somehow compute it correctly. I don't know if that helps. Okay. Good. So now I'll try to sketch this result, and afterwards, if we have time, we'll talk about randomized as well. Okay, so before I say, I should say some password. So I told you this notation for n-fold XOR. I didn't tell you this n-fold. So this is a notation for n-fold repetition. So here you insist that you want to compute f on each instance. So you don't just want the XOR, you want to actually compute it on each instance. Okay. And for deterministic communication, there's a result of Feder, Kushilevitz, Nauer, and Nissan from 1992. And they showed that the communication complexity of computing so for any function f, the communication complexity of computing the n-fold repetition of f, it has to be at least something n times the quantity that looks like the square root of the deterministic communication minus some log of the input. So yeah, you can already see the n times root d here. And for randomized communication, and this was for direct sum. These type of statements are called direct sum theorems, where you relate the hardness of computing n instances, one instance to the hardness of computing n instances. This was sort of the best known direct sum theorem for deterministic communication. For randomized communication, a lot more is known. So perhaps the first word in this area is due to Kalyanasundram and Schnitger, and which was further simplified by Rasborough. So they showed that computing the disjointness function with randomized communication with high probability really requires linear communication. And what is a disjointness function? So each player gets n bits, and they want to compute whether there is a bit where whether there is a coordinate where xi, yi are both here. Okay, so it's this OR of ands, and this OR of ands is one exactly when there is at least one coordinate I where xi equals yi equals. And it's called disjointness because if you think of the inputs as sets, this is zero if and only if they are disjoint, if the sets are disjoint. This is the disjointness function. And already you can see some composition going on here. And these techniques were a lot of people built on these techniques to prove direct sum type results, direct sums, direct products, and XOR lemmas. So I'll show you like 3 sort of very relevant works to our result for randomized. Then we'll go to the proof for the deterministic one. So C here will be the communication for one copy. Okay. And I'll relate these quantities, the success probability to compute the n-fold repetition, the advantage to compute the n-fold XOR, with the communication that you're allowed. So T will be somehow related to N and C, and we'll see how much you need T to be if you want some reasonable numbers for the success probability and the advantage. So the first like direct sum result in randomized communication was due to Rao and Rao. So they showed that firstly F requires C bits to be computed with probability at least 2/3. If you want the same 2/3 probability to compute the n-fold repetition, then you need at least square root n times the communication required for one copy. So that's about they got for the n-fold repetition. And for the n-fold XOR, they showed that if the advantage has to be constant, then you really need root n times C bits. And this result was improved by Brewerman, Weinstein, Rao, and Iyer. And they showed that if you want even exponentially small success probability, so this is the success probability you get if you repeat the naive computation n times. So if you want even exponentially small success probability, you need that same communication lower bound, root n times. And very recently, Huochen and Yu proved an XOR lemma for special kinds of protocols. So he considered bounded round protocols. So these protocols are only allowed R rounds of interaction. So he showed that if you need C bits to compute F with advantage 1/3 with R round protocols, then to compute it, then to get advantage exponentially small, with again R round protocols, you need communication that's roughly n times C divided by some R to the R. So if you think of R as a constant, you really need linear envelope in the communication to compute with constant rows. So this was Huochen's work, and then we generalized his ideas together with the ideas in the previous works to show the result for general protocols. So we showed that for general protocols, if C is the bound you have on communication, then to compute the n-fold XOR with exponentially small advantage, you need root n times C. That is how these results are related. Okay, so questions? Okay, so then I'll go to the high-level ideas in the lifting result, and what it is. So for simplicity, let's assume that G is actually just the OR on n instances. This is with loss of generality. This is not, so you lose something here. But I'll tell you how you can use the same ideas if G is an arbitrary. Okay. So note that the sensitivity of G is n, because the OR on all zeros is 0, but if you flip any coordinate, the OR becomes 1. Okay. And in this case, we want to show this result, which is that the communication complexity of the n-fold OR is at least n times the communication required for F divided by log of F. And the key lemma here is going to be that we're actually going to show that, let's say to a contradiction, there is a cheap deterministic protocol that computes the n-fold OR, like a really short protocol. Then we're using this protocol, we're going to extract a large rectangle for F, which is constant. So if the n-fold XOR can be computed cheaply, we'll extract a large rectangle for F, that's constant.
Wait, that's the notation is XOR.
So n-fold, sorry, n-fold OR. If you compute the n-fold OR cheaply, then you'll get a constant. Then you'll get a large rectangle for just f, which is constant. Yeah, the parameters will get into later, but you'll just get a big monochromatic rectangle for f in combined rectangle. And I want to say like a few words about how you get the theorem from the lemma. So this is the theorem and this is the lemma. Okay, so this uses an idea of Nissan and Wigderson from '95. So let's let R be the rectangle promised by this lemma. So again we're assuming the n-fold XOR can be computed cheaply. So there's this big rectangle. And let's write the matrix for F in this manner. So R I've written on the top, right for me. Yeah, it's one of those. R, and then the remaining things are A, B, and Z. And what they observed was that either the rank of the submatrix RA or the rank of the submatrix RB is at most half the rank of. So the rank goes down for one of these submatrices.
Whatever dimensions of R.
So R is just big density. It could be like some rectangular submatrix. It's just the size of that matrix relative to the matrix for F is large. I'm not saying anything about the dimensions. And so this gives you an intuition for how to construct a protocol. So first, the players are going to write the matrix in this manner. And let's say that we are in this case, that the rank of RA is at most half the rank of F.
Okay. This is not the sketch of the key lemma.
This is a sketch of the theorem
using
the key lemma. So let's say that the rank of RA is at most half the rank of F. So now Alice will tell Bob whether or not her input is consistent with these rows. If it is consistent, the players will recurse on the RA submatrix and the rank has gone down by half. If it is not consistent, they will recurse on BZ and the size has gone down because R is dense. So they'll replace this matrix MF with RA or BZ. In one of the cases, the rank goes down. In the other case, the size goes down. And so this can only happen some number of times before you hit a constant matrix. And what you're going to end up, if you do this protocol, is that whenever the rank goes down, the communication becomes much lesser, becomes much lesser. But if the size goes down, you don't get you get some win, but not the same win as when the rank goes down. And so this protocol, it's sort of very unbalanced. However, you can show that the number of leaves in this protocol is small. So this protocol is quite deep, but the number of leaves is small. So you can balance the protocol to get like a cheap deterministic. And if T is really small, then you will get a contradiction. You will get that the communication is smaller than DF. So that's why T has to be large. So does this make sense? Okay. So now let's try to prove the lemma. So this is what we want to prove. If the n-fold OR can be computed cheaply, then there is a large constant rectangle for F. Okay. So let's see. So the first thing we'll observe is that there is a large monochromatic zero rectangle for the n-fold OR. Okay. So the size of the rectangle is the number of zero inputs for the n-fold repetition of F divided by 2. And the reason is the following. So there is a cheap protocol for the n-fold OR. And the protocol has communication at most T, which means at most 2 to the T leaves. all these 2 to the 3 leaves, they partition the space of, certainly they partition the whole space, but they also partition the space of the 0 inputs. So there must be one rectangle which accounts for a large part of the 0 inputs. So here, this notation f inverse 0 to the n, this is the set of all inputs xy, such that f of xy is 0 in each coordinate, which makes the OR 0. And in pictures, what's happening is, so there's this space of the inputs where each coordinate is 0, and there's going to be a large rectangle of size this much that's completely inside the set. Okay, and using this rectangle, we are going to extract the rectangle for f. And the idea is that we're just going to project this rectangle r tilde onto one coordinate, and there will be some projection that's large. So these are the projections. So r tilde I is just all the inputs in the ith coordinate, such that there is some input in r tilde where the ith coordinate is xi by I. So these are the projections. So these are and the observation is that r tilde is a subset of the Cartesian product of the projections. So everything in r tilde is contained here, which means that since r tilde is large, one of these projections must be large. So since r tilde is large, at least for one of the projections, the size is a 1 over nth root, 1 over nth root of the size of r tilde. So you take r tilde and you project it on every coordinate. One of the projections must be large, and it is actually a 0 rectangle because every xi appears as some input for r tilde. So it's a large all zeros rectangle. And so if the density of 0 inputs is at least that number 1 over 4 times the square of the rank, we have proved the lemma. But if not, f, what we can say is that f is a small rank matrix, and the number of 0 inputs is really tiny. It's like less than 1 over 4 times the square of the rank. So it's like a small rank matrix which has lots of 1 entries, almost all ones matrix. In this case, you can ignore all of this and directly extract a constant density rectangle for f. So there's a word called Levinsky and Levitt. What they show is that if you have a small rank matrix and it's extremely biased towards 1, then the matrix will contain a huge, like a constant density monochromatic. So this is the basic idea. So you keep trying to extract 0 rectangles for f using the protocol, and when you fail, it must be because you're really biased, in which case you can ignore the protocol and just get a constant density. Any questions? So this is so the reason for the 4 times rank squared is really because of this biasness. Yeah.
And this is a one direction thing. It's
by direction. You can say the same thing.
Okay. So why did you start looking for a 0?
Because that's because of OR. So if you have a 0, if you have a 0 rectangle for the n-fold OR, that means every coordinate should be all zeros. Yeah. So that means that r tilde is really contained in this set. And this property will break when we go to compositions. So I'll go to compositions now, general compositions. So in general now, the OR is replaced by some function g, and I'll just assume that g has sensitivity n. So that's the only assumption we make. And so let's take some input which is maximally sensitive for g. So z, this special input z has the feature that if you flip any coordinate, g, the function value g flips, while keeping the others in. And let's look at this distribution, the specific distribution, where you sample xi by I in each coordinate independently, subject to the condition that f of xi by I is exactly equal to zi. So you only want to be in the looking at inputs where f of xi by I is zi for every coordinate. Okay. So again, so first observation is that, like before, there is a large rectangle. There is a monochromatic rectangle. This time it's monochromatic for G composed with F, whose density under this distribution is 2 to the negative T. So there is a protocol with T bits of communication, which means the rectangles, due to the leaves of the protocol, they partition the space of inputs, and some rectangle must account for at least 2 to the negative T amount of measure under P. And let's see in pictures what's happening. So there's this set. Previously, it was the f inverse 0 to the n, but now it's the support of this distribution. And now you get a rectangle which accounts for some reasonably large portion of this support. Previously, we had r tilde being completely contained, but now that may not be the case. And what we are going to do is we are going to zoom into this shaded region. And from that shaded region, we'll extract a constant dense rectangle for for F. That's sort of what we'll do. So we'll find a suitable projection of this shaded region to a single cone. And I'll tell you how to do that now. So this is just our setup from before. So Z is the special input, P is this distribution, and R tilde is the rectangle that witnesses lots of inputs under P. And the key claim here is that if I take any coordinate I, and I fix the inputs for x in the first I-1 coordinates, and fix the inputs for y in the last n-I coordinates, the support of the resulting distribution, it's actually a monochromatic rectangle for the n-fold repetition. So in the previous picture, maybe I should draw it. In the previous picture, you had this support and this rectangle here, and this shaded part. The shaded part is basically what you get when you condition this distribution on R tilde. What I'm saying is that if you fix some of the rows, those rows will be consistent with x1 through xi minus 1, and some of the columns, which are consistent with yi plus 1 through yn, that set becomes a rectangle. There's a reciprocal. And so another way of thinking about this is that look at this distribution P of xy conditioned just on R tilde. So here the x and y's are quite correlated. Like x and y are correlated with themselves, xi, yi, but they might also be correlated across coordinates. Fixing this input breaks the dependencies across x and y. That's what this says. Like you can show, the same proof will also show that xy become independent under this. But yeah, so now I'll try to show you why. Does this make sense? Okay, so let's take two inputs, x prime, y prime, and x star, y star in the support. To show that this is a rectangle, we want to show that x prime, y star, and y prime, x star are also in the support. Would be a rectangle. And we also want to show that it's monochromatic, but the proof will show that. Okay, so let's write down x prime. So I've just written down x prime in n blocks, one for each coordinate. I've written down y star in n blocks, one for each coordinate. For x prime, y star to be in the support, it has to satisfy certain conditions. So firstly, x prime, y star has to be in the rectangle R tilde. But that is certainly the case because x prime, y prime, and x star, y star are in the rectangle. So x prime, y star is also in the rectangle. Another thing is that x prime, y star has to be consistent with this fixing. That is also the case because x prime y prime is consistent and x star y star is also consistent. Okay? And so in particular, what you can say is that x prime 1 is the same as x star 1. X prime 1 and x star 1 are the same as x1. So just write it down. And the same holds for x prime 2 all the way up to x prime I minus 1. They're all the same as x stars. And the same also holds for y star and y prime in the last n minus I coordinates. And a consequence of this is that the function value for x prime y1 star is actually z1. This is z2, and so on and so forth. Because x prime is the same as x prime 1 is the same as x1 star. And so what this means is that the function value is z1, z2, all the way up to zi minus 1 in the first I minus 1 coordinates, and zi plus 1 through zn in the last n minus I coordinates. But now if x prime I star was 1 minus zi, this g of f would flip. So we assume that R tilde is a monochromatic rectangle for G composed with F. But now, if this was not Zi, if this was 1 minus Zi, then on this input, G composed with F would flip, which means that the matrix is not monochromatic for G composed with F. So if x prime, so this means that x prime y star is also in the support of this distribution, which means that it's in the support of. So, this we have shown that it's a rectangle, and the proof also shows that actually for every input in this rectangle, the function value is just z. The function value of the n-fold repetition is always just z. Might have gone a bit fast there, but I can explain. Yeah, so basically everything here has to evaluate to z. And because R tilde is a monochromatic rectangle for G composed with F. And how do we use this fact? So what we show is that there is in fact a coordinate I, and there is a way to fix the inputs x1 through xi minus 1 and yi plus 1 through yn, such that the density of this distribution, just the xi yi, is large. It's sort of what we wanted to do. I'm not going to get into the proof of this claim. It uses entropy. It's not super hard. I can explain to you later. But the basic idea is that this distribution has like large support, and there will be some way to fix I and coordinates and their inputs in the I minus 1 coordinates for Alice and n minus I coordinates for Bob, where you still see a lot of entropy for the ith coordinate. And so the final rectangle that we want for the lemma will be the support of this distribution. So that's it. That's the lemma. Any questions? Okay. So that's the listing. I can now tell you about the XOR lemma, randomized XOR lemma. And this part will be quite disjoint from like what we have talked about so far. Quite different. So this is just be different stuff. So this is the notation that we set up before. I'll just recall what we wrote down. So the input XOR is just the XOR in n coordinates here that we saw earlier. An advantage is the advantage to compute f with c bits. This is the maximum advantage that you can get if you're only allowed c bits of communication. Advantage is this way. And the theorem we want to show is that for some sufficiently large constant c naught, as long as it is the case that to compute f with constant advantage, even with c bits, then we want to show that to compute the n-fold XOR with exponentially small advantage, we need large communication, like root n times c. Okay. So I want to sketch out the high-level approach here. What is the main idea? And this is actually going to build on some of the works that I've shown you in the related work sections. Which, I mean, you can trace it back to the result of Raspberry, but sort of want to just tell you what the approach is here. So let's say we'll again proceed by contradiction. So let's say we have like a really cheap protocol pi that computes the n-fold XOR with really large advantage. So something that's too good to be true. And what we're going to do, the main thing that we're going to do is we're going to come up with a way to measure the information that's transmitted in the protocol by the two parties. And we'll show that this measure has some nice properties. So what first we'll show is that the information that the protocol reveals is bounded by its length. So if the protocol is small, is short, it will not reveal much information. And the main thing that we will do is that we will show that using this protocol pi that solves the n-fold XOR, you can come up with a protocol for the single copy whose information is much smaller than the protocol. So the information will drop by a factor of 10. Okay. This protocol tau might have huge communication, but the information will be really small. And then what we'll do is we will take this protocol tau and then we will try to simulate it because it has small information, whatever that means. We will try to actually run it in an efficient way so that we actually have small communication. And depending on this parameter t and how good our simulation is, we will get a contradiction. We will get a protocol that's with c bits, you get much bigger advantage. So this is the high-level template. So now I have to tell you what information is and how it's used. And to do so, I want to recap this work of Barak, Blair, and Anup Rao that I mentioned earlier. And I'll tell you what measure they used and how we changed that so that it works in our case with the XOR. So this is something that I mentioned briefly earlier. So this notation pi of xym is going to be the probability distribution induced by a randomized protocol. For the remainder of the talk, I will assume that xy are sampled uniformly at random, uniformly independently at random. So let's say that this uniform distribution is a hard distribution. Let's pretend that that's the case. That might not be, but it'll make our life easier in terms of understanding and so on. Okay, so pi of xy is a uniform distribution, and then the messages of the protocol induce the remaining probability distribution. The information of pi is this expected log ratio. So I'll tell you what it means. So it's the expectation over pi of the log of the probability of seeing xy conditioned on m divided by the probability of xy. So the probability of xy, this is uniformly random. So this is like 1 divided by the size of the inputs. This number roughly looks like how big the rectangle m is. So if you have a cheap protocol, then there are lots of big rectangles. So the numerator is going to be quite small. It's not going to be very different from this number, pi of xy, because the rectangles are huge. But if you have a really long protocol, some of the messages are going to be tiny, like they correspond to tiny rectangles. And if you know the message, then you probably know a lot of information about the inputs that belong to that message. So if you're familiar with information theory, this is roughly the mutual information. This is the mutual information between the inputs and the messages, but you don't need to know that. It's just this expected log ratio. So it tells you how much the messages are telling you about the inputs. So that is this quantity. And so they use this quantity as the measure of information to carry out the ideas in the previous slide. And one thing you can show is that for this measure, the information is bounded by the length of the protocol. And this is not too hard to show. but let's just assume that's the case. The hard part is the second step, which is suppose you have this protocol for the n-fold XOR, which is really good. How do you construct this protocol for the single copy, which is which with small information? So that's the second step. And I'll try to tell you how they did it. And let's just, again, for simplicity, let's assume n is 2. So you have a protocol for the two-fold XOR, and we will use that protocol to come up with a protocol for each copy, for f in each copy. So now x is going to be 2 inputs, one for each coordinate, x1, x2. Y is going to be 2 inputs, one for each coordinate, y1, y2. And we will construct two protocols. It's a protocol pi1 will try to solve f in the first coordinate. And protocol pi2 will try to solve f in the second coordinate. Okay, so in the first coordinate, Alice and Bob get x1 and y1 as inputs. They want to compute f of x1, y1. Here's what they do. They will sample the shared randomness of the original protocol pi, and they will, in addition, sample y2, the input for Bob in the second coordinate. Okay, and Alice is now going to privately sample her input in the second coordinate. So now the players have enough information to run the protocol pi. Anytime Alice wants to send a message, she knows x1, x2. She also knows the shared randomness. So she knows what she can just run the protocol pi. So she can send the first message. Bob knows y1, y2, the transcript up until that point. So he can send the second message. So they have enough information to run pi. They will run pi. At this point, they both know f of x1, y1 XOR f of x2, y2. They both know this value. And so now Alice will just send f of x2, y2, and Bob can XOR that. So Alice knows x2 and y2. So Alice will send this bit, and the players can XOR that. Bob can XOR that with the thing that's computed by pi to compute f of x1. And send this additional bit and get the XOR to this point. So this is pi1. And pi2 is very similar. The roles of Alice and Bob will just change now. So Alice, in this case, they want to compute f of x2, y2. Alice gets x2, Bob gets y2. This time, they will sample x1 in the shared randomness, and Bob will privately sample y1. Again, they have enough information to run the protocol because Alice knows x1, x2, m0. Bob knows y1, y2. He knows more, but no. And they'll run the protocol. And this time, Bob will send f of x1, y1 because he knows x1 and y1. And they can XOR it with the XOR, and they'll compute. So these protocols for x1, for the first and the second coordinate, they're, the communication is really large. It's as large as the n-fold XOR. But it turns out that this information quantity for one of them has to be small. Okay. So let's write down the information quantity. So the information for the first protocol is, again, an expected log ratio, where you sample x1, y1, condition on the transcript. So this time, y2 is part of the transcript because it's shared randomness, divided by the probability of seeing x1, y1. And the same thing for pi2. It's not super important like what these things are. Just the most important thing here is that these two numbers add up to exactly the information of pi. So that's a fact that you can show. So this is uses this fact that I told you. If you have a product distribution, then conditioning on a rectangle preserves the product distribution. So just take my word for it that these two quantities perfectly add up to the information of pi. And in particular, what this means is that for one of them, the information must be at most half the information of pi. These quantities are non-negative, so one of them must be at most half. And now you can proceed with that coordinate. And one thing I should note here is that let's go back to the protocol that I had written previously. So note that both protocols, pi1 and pi2, they will succeed if and only if pi succeeds. So if pi succeeds in computing f of x1 y1 XOR f of x2 y2, then this protocol will succeed to compute f of x1 y1 because Alice will XOR the f of x2 y2 with the correct bit. And the same thing for the first coordinate. So both these protocols succeed if and only if pi succeeds. And as a consequence, if the original protocol succeeds with exponentially small probability, then you can't really say much. Like then the protocol pi1 or pi2, whichever one has small information, it will only succeed with exponentially small probability. What we want to show is that we want to get some win in the advantage. Make sense? Okay, so this was the issue that Cheng Yu also had in his work. And he had a very nice idea that resolved this. And that led to some really nice definitions. And so I just want to tell you those definitions. So here's what he observed. So let's fix x1, y2, and the messages of the protocol. So let's just fix them. So the quantity that I've written here, this looks like the advantage conditioned on the fixing. So I've fixed x1, y2, and m. The inner part is the advantage, and this is the advantage condition on this fixing. What he showed is that what he observed is that this quantity, it's actually a product of expectations. So once you fix x1, y2, and m, the inputs become independent. And so this is actually a product of expectations, which means that if this quantity looks like 2 to the negative n, one of these must be 2 to the negative n over 2. That's sort of. So in one of the terms, you'll witness an increase in this advantage. So this term looks like the advantage for the first coordinate, and that term should look like the advantage in the second coordinate. So that's the main idea. So what he's then noticed was that there is a large set of these triples, x1, y2, m, where let's say in the first coordinate, you witness an increase in the advantage. So this is always 2 to the negative n. One of these terms has to be at least 2 to the negative n over 2. So for each x1, y2, one of them is at least 2 to the negative n over 2. This means that for at least half of them, one of them is at least 2 to the negative n. And so a very natural thing to do now is let's condition on these triples. So if we witness an increase in advantage here, let's just work with these x1, y2, m's. Okay. So the main issue is that once you condition on this set, the protocol structure can break. So in the protocol, a past message can never depend on the future message. But if you take the distribution induced by a protocol and condition on some set, that structure can completely break. So that does happen. However, he noticed that these sets still have a lot of interesting properties, and he was able to use those properties to get something meaningful. So these are these type of sets. They are what he calls rectangular sets. And a rectangular set is a set with the following feature. Once you fix the messages, the set becomes a rectangle. You fix any message, the set becomes a rectangle. So this is a rectangular set. I should say why the previous example was a rectangular set. And there's also a rectangular distribution with similar properties. It's a rectangular distribution. It's a distribution which you can write as follows. It's the input distribution times some function which only depends on Alice's input and the message, and another function that depends only on Bob's input and message. And I'll say why you care about these things, but basically these things generalize protocols and rectangles, these two things. So this generalizes rectangles like from the protocols, and this generalizes protocol, the distribution induced by protocols. And in the work of BBCR, what they were doing is that they started with a protocol and they found a protocol that's better for one coordinate. Now we're going to give up on the hope of finding a protocol that works for one coordinate because we want to witness an increase in advantage. We're going to work with these general distributions and hope to approximate protocols using them. So as we saw in the previous slide, using these rectangular distributions gives you some win in the advantage. Like using these rectangular sets, you witness some win in the advantage. I should say, any set that depends on just x1, y2, and m can be written in this way. Because once you fix m, it only depends on x1 and y2, which is a product set. So these sets are nice in this manner. So let's see what we can do. So maybe I'll have a picture here. So this is what I told. This is like how a protocol looks. This is the message. This is the structure induced by a protocol. A rectangular set might look slightly different. Like within each message, you might have like a smaller set where you get a win in the advantage. So this is sort of picture should maybe. It's a good thing to keep in mind. This might be how a rectangular set might look like. You're allowed to throw away inputs in each rectangle. And so let me tell you some nice properties about rectangular distributions, which really make everything work. So firstly, they have this closure property. So if S is a rectangular set and Q is a rectangular distribution, then when you condition Q on S, it remains a rectangular distribution. So a protocol is also a rectangular distribution. It's not hard to check. And in particular, if you condition the protocol on a rectangular set, you get a rectangular distribution. So that's nice. And another nice fact, so this we used earlier, we showed that if once you take a protocol and you fix x1, y2, and m, then the inputs become independent. This feature is again preserved by rectangular distributions. So this we use to show that the advantage goes up. This is again preserved in rectangular distributions. And the last thing is that let's pretend that the rectangular distribution really looks like the original protocol conditioned on a rectangular set. Pretend for a moment it looks like that. Then it's easy for the players to sample this distribution. They'll run the original protocol, and each player will check if they are in the rectangular set. And they will accept if and only if they're in the rectangular set and reject otherwise. So they can use rejection sampling to basically sample according to Q. So you want to do some rejection sampling because you want to sample you want to accept according to the density of. So these are some really nice facts about this things. And which time that? Minutes. Okay, so I might have some time at the end, but maybe we can stop early. Anyway, so I'll now tell you why these things are nice and how to use them. Okay. So the message here is that protocols are nice. It would be nice to keep working with protocols, except that we don't get a win in the advantage. Working with rectangular distributions, we get a win in the advantage. So maybe we can trade off, these. So these rectangular distributions are generalizations of protocols. So maybe we can approximate protocols by these rectangular distributions while getting a win in the advantage. That's the basic idea, and that's where marginal information comes in. And so this is the new notion of information that we used to prove the XOR. Okay, so to tell you about what marginal information is and connect it with everything that I've said before, let's first fix a protocol pi, and let's fix a function h. H is a Boolean function. And this marginal information is this quantity. I'll tell you what all of the terms mean. So it's the infimum over all rectangular distributions of a quantity that looks like a max of 3 terms. So this log ratio q over pi there is a different log ratio, and then there's a term that looks like the advantage. So the last term, if you think of it as advantage. Okay, so what's really going on here? So pretend for a moment that Q is actually pi. So if Q is really pi, then this term is just 0. And this is the log ratio of the information term that we saw. So pi of x, expected log of pi of xy divided, condition on m divided by pi of xy, that was exactly the information term. So this is somehow capturing the information under Q. And this term captures the advantage of computing H under Q. Sort of what's really going on. So, and the first term is sort of measuring how far Q and pi are. So imagine Q is now a protocol conditioned on a rectangular set. So imagine Q is really just pi conditioned on a rectangular set. Can you see that? If that is the case, then this ratio is just the density of R. So if the rectangular set is large, this number is small, and otherwise it's large. So sort of what this time is trying to do is that, okay, I'm allowed to not look at protocols anymore. Let's look at rectangular distributions. There's a price I pay, which is that this approximation, the approximation between Q and pi can become large. But for the price of that, maybe I can get a big win in the advantage. That's sort of the trade-off that's going on here. So now you're no longer restricted to choosing protocols. You can choose rectangular distributions, which will, consequence of that is that now this approximation of the protocol by the rectangular distribution could be bad, but maybe you get a huge win in the advantage. And that offsets the price. So the first quantity sort of measures how far Q and pi are, how good Q is to approximate the protocol. The second sort of, you should think of it as revealing the information that's revealed by messengers. And the third is capturing the advantage under Q. So the marginal information is like really trying to optimize over, optimize over all these quantities. How much advantage can I get if I sacrifice some this protocol structure while also trying to make sure that the information revealed doesn't blow up. So what's happening? And the main thing that we show is the step that I told you before, which is given a protocol for the n-fold XOR, extract out a protocol for a single copy with small information. So this step is called subadditivity. So again, this is the marginal information. I should tell you, so I forgot to say what I is. So I is just a parameter that makes sure that all these numbers are the same scale. So these numbers could be different, but I is a parameter that we can choose so that these three numbers are roughly the same. Don't worry about that. And the main lemma here is that, say we have two functions, f1 and f2, two Boolean functions, f1 and f2. And let's say that we have a protocol pi that computes f1 XOR f2. Now we ensure that there are protocols pi1, pi2, such that the marginal information of pi1 to compute f1, or the marginal information of pi2 to compute f2, one of them goes down by a factor of half. At least one of them goes down. So previously you had the information terms add up perfectly to the information of pi. Now you show that there is some protocol which gets half the marginal, whose marginal information drops by a factor of 2, roughly. And then you can recurse for that. Okay, so basically what we're going to do is like, imagine n is just a power of 2. So we will split n into two equal parts. And for one of them, we will get a protocol pi1 whose marginal information goes down by a factor of 2. And we'll keep doing this to end up with a protocol for a single coordinate whose marginal information will become. So initially, this number will be like n times I. And finally, we'll end up with just order I. It's going to be 1 over n fraction of the initial number. So this is the main thing. I am not going to get into the proof of this. Maybe we can talk later on. And maybe I should, might be good to end here. I know I have a ton of time, but maybe I can take questions instead of saying. So a couple of questions. So one is, we showed an XOR lemma. What can we say if we replace XOR with OR? So is the following true? So is there, for a sufficiently large C, is it true that if the best protocol with at most C bits succeeds with probability at most 2/3 to compute F, then to compute the OR of F on n copies with just 2/3 probability, you really need root n times C its computation. That is one problem. Like, so this is one for randomized communication, and another one for deterministic communication is this problem. It's actually due to, they raised it in the work of Kashmir, Raz, and Richardson. So this is the connection I mentioned between circuits and games. So for any circuit, you can define the Kashmir-Richardson game. So in this game, Alice gets a 0 input and Bob gets a 1 input for the circuit. And they want to figure out a coordinate I where xi is not equal to 1i. That's the goal of this game. And the question is, can you show that there must exist? So we just want an existential result. Can you show that there exists a function whose amortized communication complexity of computing this relation? So this is now a relation, is super logarithmic. Yeah, and that's it. Thank you. Questions?
Where did you use this condition that you need C to be at least 0?
Yes, good. So all the way in the Barak Graham and Chan Rao thing, where I showed how to get two protocols. So at the end of the protocol, one of the players must send an extra bit to compute. So like now, if the communication of f is really small, then you need this extra bit. So the communication becomes bigger, and you have to so in the final bound, you have to account for that extra bit that you sent. So if the communication was really small, you will not get anything because that you have to subtract out the contribution from that bit.
So the C0 could be eventually like 2 or 3 or something?
Yeah, the C0, so in that thing, the C0 could be very small, but in our work, you need the C0 actually a little bit bigger. So I didn't show you, so I showed you, I said how to get a protocol with small marginal information. You have to now simulate that protocol. So in the simulation, again, you lose something. So you pay some extra communication in the simulation. So you have to again account for that. So it's actually bigger. Somebody else, maybe there's no one else.
Well, I have one question about your definition of marginal information.
Yeah.
Like, there's a factor of 180 there. Is this like, do you think this is the right thing, or is this something that works? Like, do you think
I think
should be?
I personally think this is the right thing. In the sense that I think, for example, to get some result for the OR of n copies of f, something similar might work. Because you sort of want to trade off, you want to be able to not just have the freedom to not just work with protocol distributions, but access this bigger space of rectangular distributions. It might be the case that there is a different, this might change now. You could play around with this. You could change this set, and that will basically allow yourself to use more, to not just use protocols, but use other distributions, in the hope that you get a big win in the probability of success, but for the price that you are now not really close to a protocol, but you can make some far away. So I think this gives you that freedom to play around with this trade-off.
And how did this come up?
So U's work has a similar potential. So he uses a potential. So you can think of this as a potential function, actually. So initially, the potential function starts off as n times I, and you keep doing some operation, and then potential function goes down. But his potential function had the feature that if the potential function is small, you don't get a protocol. You need some additional properties to get a protocol. So this thing has the feature that if it is small, you actually do get a protocol at the end. So it's like an information measure in that sense. I should say that Amir, in your paper with Anup and Weinstein and sorry, yes, they used a similar quantity. So they again also went away from protocol distributions. They considered protocols that are close to having small information, if I'm correct. So they expanded the set of distributions that they could use. And instead of just looking at protocols, they looked at a bigger class of distributions. So it seems like this is actually useful to actually look at a bigger class of distributions than just protocols. Yeah. I don't have any other things to say.
Thanks a lot.
Thank you.